So let us now solve this question. Now just understand that what they are asking. They are saying number of linearly independent eigenvectors that are possible here, given this characteristics equation. Okay, first can you tell me what is the dimension of the matrix corresponding to this characteristic equation has been came? It must be 2 plus 1 plus 3, which means the matrix must be of dimension 6 cross 6. Then only you got degree 6 characteristic polynomial, right? Because the matrix must be the dimension 6 cross 6. See, the polynomial that we make is basically like a minus lambda, like that, right? So basically, if it is lambda power 6, the determinant is lambda power 6, it must mean that that it is basically 6 cross 6 matrix. Okay. Anyway, coming to this point, that how many linearly independent eigenvectors that you can have. Now, as I told you that if you have different eigenvalues, which means here you have 3 different eigenvalues, right? So maybe I can just go to the next page, and here let me just tell you that how many different eigenvalues you have. Here you have 3 different eigenvalues. One is lambda equal to 1. Another one is, which is repeating 2 times, that's okay. I mean, if you want, I can write something like this. Another one is 5. Another one is 7, right? Which is repeating 3 times. So basically you have 1, like 1, 5 and 7. You have 3 different eigenvalues. Now, using these 3 different eigenvalues, that is for sure that you will be having at least 3 linearly independent eigenvectors. That is for sure, because 3 different eigenvalues you have. Now, corresponding to 1, you can have at most 2. Corresponding to 5, at most 1. Corresponding to 7, at most 3. Because lambdas are not equal here, right? If lambdas is not equal, then you can have at most 3, minimum 1, obviously, right? So at most 3 you can have here. At most 1, at most 2. So basically, if someone asks you how many different linearly independent eigenvectors that you can have, then at most this 6, always, because it's 6 cross 6 dimension, then at most you can say at most 6 linearly independent. Why? Because there are 6 eigenvalues that you have. Because of the 6 eigenvalues, you have at most 6 linearly independent eigenvectors. And since out of them only 3 are unique, that is why at least 3 you have, right? So I hope you understood. See, because of these you have 3 linearly independent. Because of these you have 6 at most. 3 minimum 3, 6 at most. So that's how you can solve this question, right? I hope you understood. See, here the answer will be at most 6, at least 3. This is the answer. So B and D is the correct answer. Now in general, I can say that if you have, let's suppose, a characteristic equation which is lambda minus lambda 1 power m1, suppose, into lambda minus lambda 2 power m2, okay, and let's suppose there are k lambdas, maybe lambda minus lambda k power mk. Let's suppose there are k lambdas, and if someone asks you that from this what you can infer, then you can say that since there are k different lambdas, so there are at least k linearly independent eigenvectors, and I can say at most, let's suppose the summing of this is actually n, m1 plus m2 till mk. Let's suppose this is n. There are at most n linearly independent eigenvectors, right? So that's how you can understand this particular problem. I hope that is fine to everyone. So okay, let me just give you more example. Probably, suppose if I just ask you lambda minus 1 into lambda minus 2 into lambda minus 3. So you will say that there are 3 different eigenvalues. That's why 3 linearly independent, okay, 3 linearly independent eigenvectors, and because the power is 1, then the eigenvector is exactly 1. Basically, I mean, at least and at most both are same here, because the power is 1. So that's why the number of linearly independent eigenvectors corresponding to 1 is just 1. Here also 1, here also 1. So I can say that exactly 3. Okay, exactly 3 here. Let me give you more examples. Maybe let's just see a couple of more examples so that you understand it very well. Okay, lambda minus 4 power 4, lambda minus 6 power 6. Now here, okay, let's suppose lambda power 5. Suppose something like this. Here you will say that you have how many different eigenvalues? You have 1, 2, 3, 4 different eigenvalues. So you will say that at least, okay, at least I mean, actually, exactly you don't know until unless you have all the information. But given this particular equation, you can say at least 4 linearly independent eigenvectors. Now, because of lambda equal to 0, see here the lambda is 0, right? If you want, I can write something like this. Lambda minus 0 power 5 instead of lambda power 5. If you want lambda minus 0 power 5, I can write something like this. So here you can say that at least 4, because 4 different eigenvalues you have. And because of lambda equal to 0, you can have 4 lambda equal to 0, number of linearly independent eigenvectors could be just 1, just 2, just 3, just 4, just 5, something like this. Can it be more than 5? No. Can it be 6? No. It cannot be 6. So corresponding to lambda equal to 0, it could be 1 to 5, anywhere between 1 to 5, at most 5. If the power is 5, then at most 5. Okay, so we will see with more examples, don't worry. But here I'm just telling you that if power is 5, then at most 5 linearly independent eigenvectors you can have. Similarly, power is 2, then at most 2 linearly independent eigenvectors you can have. Let's do one thing. Let's see more examples, and then we will come back to this again. Okay, so that you understand this very clearly. Let's solve for this particular example. Okay, for eigenvalues and eigenvectors. Now, if you want to solve for eigenvalue, then you need to do this 0, 0, 1 minus lambda, right? And then equal to 0. So from here you can say 1 minus lambda power cube equal to 0. So lambda is repeating 3 times. Lambda equal to 1 is repeating 3 times. So 1 is basically you are getting 3 times. Now let's just see that, okay, 1 is getting repeating 3 times. Based on till now what we have discussed is basically that if you have lambda minus 1 power cube, then in this kind of characteristics equation, if you have something like this, then the number of linearly independent eigenvectors corresponding to lambda equal to 1 could be just 1, could be 2, or could be 3. It cannot be more than 3. Let's just see in this particular example how much you are getting. Okay, so let's just see in this particular example how much you are getting. Now let's just calculate eigenvector for lambda equal to 1. Okay, so this is the matrix that we have. Now can you do it? Maybe let me just try doing it. Okay, so for lambda equal to 1, you will be writing minus 1, minus 1, minus 1. So basically you are getting, okay, this is 0, 0, 0, 0, 0, 0, 0, 0, 0, right? And this is the b you got. Now you want to solve for bx equal to 0. Can you do it? As you can see that x1, x2, x3 all are the free variables here. So you can make them stu. So you can say that x1 equal to s, x2 equal to t, maybe x3 equal to u. Which means that finally you got a vector which is just like this, stu. Now can you rewrite it? Let me just try doing it. So this is stu, and then if you want to rewrite it, you can just write it like this, s into 100 plus t into 010 plus u into 001, right? So you will be writing something like this. Now this is a set of eigenvectors corresponding to lambda equal to 1, if you remember, right? Just see, corresponding to lambda equal to 1, we got this set of eigenvectors. Now corresponding to lambda equal to 1, how many eigenvectors you got? 3 linearly independent eigenvectors you got, and lambda is getting repeated 3 times. I told you that at max you can get 3, but this is such an example where you are getting exactly 3. That's okay. I mean, that's fine. But yeah, at least that is, I mean, that is understood that, okay, I cannot get more than 3, but yeah, at most I can get 3, which is where it is, which is what it is shown in this particular example. So this is one example where lambda is repeating 3 times. I am getting 3 linearly independent eigenvectors. Let's just do one more example, then one more example. I will show you 3 examples, and in those 3 examples, I will just ask you to observe something. Okay, let's just see one more example. So here, just calculate the lambda that you want to calculate for, I mean, the eigenvalues. So it will be 1 minus lambda, then 0, 0, 1 minus lambda, right? Now let's just do one thing. Let's just solve this equation. So I think I can expand with respect to this. It will be 1 minus lambda into 1 minus lambda. I think this will be just 0. So I think it is again 1 minus lambda cube, right? It is again 1 minus lambda cube, which means lambda is again repeating 3 times, which means lambda equal to 1, 1, 1. Okay. Now you got 3 lambdas, or all the lambdas are same. That's okay. Now, if you have lambda minus 1 power cube equal to 0, lambda 1 minus lambda power cube equal to 0, I mean if you have degree 3 polynomial, which means lambda equal to 1 is repeating, let's suppose 3 times, then in this case, we know that at most 3 linearly independent eigenvectors you can get. But let's just see in this case how much you get, right? I mean at most 3 you can get, but let's just see in this case how much you get, right? Let's just see this. Okay. So now what you can do, you want to calculate the eigenvectors for lambda equal to 1, right? Eigenvectors for lambda equal to 1. So it will be 0, 0, 0, 0, sorry, it is 1, 0, 1, 0, 0, 0, right? I mean this is the matrix B that you have, and you want to solve for Bx equal to 0. Okay, so let me just rewrite it using the elementary row transformation. I mean, let me just exchange these 2 rows, and then you will be having 1, 0, 1, 0, 0, 0, 0, 0, 0, right? Only one pivot is there, so that's why you will say that okay, x2 and x3, let's suppose s and t, and then x1 will be just opposite of x3, which is minus t. So finally, you got something which is s, t, and minus t. This is the vector that you got, which is the eigenvector corresponding to a set of eigenvectors corresponding to lambda equal to 1, right? So eigenvector corresponding to lambda equal to 1. And remember, lambda was repeating 3 times. Now, if you just rewrite it, how many linearly independent eigenvectors you have? Since there are only 2 free variables, I think you know the answer. Since there are only 2 free variables, that's why like you have only 2 linearly independent eigenvectors, right? Only 2 linearly independent eigenvectors, which is just looking something like this. So these are 2 linearly independent eigenvectors. I hope you understood. Now see here, if lambda is repeating 3 times, then also you got just 2 linearly independent eigenvectors, but earlier you got 3. That is fine. Let's do one more example, then I will just summarize all of these 3 examples. Let's just do this example also. Okay, so let's just solve for the lambda. This will be 1 minus lambda, 1, 0. Then this is 0, 1, 1 minus lambda. Sorry, this is 1 minus lambda, 0, 0, 1 minus lambda, right? Okay, now let's just expand with respect to this, maybe. Okay, this will be 1 minus lambda. Yeah, again this is 1 minus lambda cube, so equal to 0. So this is again 1 minus lambda cube, which means that lambda is again repeating 3 times. Okay, and lambda equal to 1 is only repeating. I made this example such a way like that lambda is actually repeating 3 times, and you get the different results with respect to eigenvector. So let's just now calculate the eigenvectors, right? Okay, so let's now calculate. Let me just copy this. Just a second. Yeah. Now let's just calculate the eigenvectors for lambda equal to 1. It will be 0, 1, 0, right? So let me write eigenvectors. So this is the matrix B or A minus lambda, whatever you want to say. So this is 0, 1, 0, 0, 0, 1, 0, 0, 0, right? Okay, now let's just see the free variables. So here you just notice that this is the pivot, this is the pivot. Okay, am I right? Yeah, there is no pivot here. This is already in the equivalent form, and these 2 are pivot, right? Okay, so you can say that x3 equal to some free variable k, x2 equal to, sorry, the free variables is x1 equal to k, x1 is equal to k, x2 equal to 0, x3 is also 0, right? x3 is also 0. Like you can easily calculate from here, and then finally you got the vector which is k0, 0. This is the set of all eigenvectors corresponding to lambda equal to 1, right? So which means that here how many linearly independent eigenvectors you have? K0, you can take common 1, 0, 0. How many linearly independent you have? You have just one linearly independent. although lambda was repeating 3 times, if you remember, lambda was repeating 3 times, still you just have one linearly independent, right? So we have seen 3 examples where in the first example lambda was repeating 3 times, right? And then 3 linearly independent eigenvectors. In the second example, lambda is repeating again 3 times, right? And then 2 linearly independent eigenvectors. In the third example, lambda is repeating again 3 times, and then 1 linearly independent eigenvector, right? I hope you understood all of this what I'm saying. So from here what you infer is that if lambda, I mean the characteristic equation is having power 3, then at most 3 you can have, sometimes 3, sometimes 2, sometimes 1. See, to be honest, I have not given any proof of this, which means that I just shown you the examples. Okay, I have not given the proof that okay, 3 more than 3 is not possible or something like that. Okay, but that proof is actually not required. With the examples you can say that okay, this is sometimes 3, sometimes 2, sometimes 1. I have not given the proof. Reason being is that proof is not required. If the proof is not required, then we will not introduce the proof at all. Okay, actually proof is little complicated, so that's why I just want to avoid it. But with the example, I hope that is clear. So you can say, now if I go back to those kind of examples again, these kind of examples, if lambda is here 1, 2, 3, 4, then you can say with the 4 different lambdas you will be having at least 4, but at most just because of lambda equal to 0, at most 5, at most 2, at most 4, at most 6. So if you just sum all of this, then 10 plus 5, 15, and 2, 17. So at most 17 linearly independent eigenvectors you can have. More than 17 is obviously not possible. Okay, and at most 17 you can have. I hope that is fine. Let me just do more questions. Probably by that you will be more convinced. Suppose if I just ask you lambda minus 1 power 3 lambda power 5, in this how many linearly independent eigenvectors you will be having? And if I just give you the options, one is that at least 2, at least 8, at most 2, at most 8. Then what is your answer? See, because of 2 different lambdas, you will be having at least 2. Because total the lambdas are 8, that's why at most 8. So that's why these 2 are the correct answers, right? So your answers are like this: at least 2, at most 8. I hope that is fine to everyone. Now let me just twist these kind of questions little bit. Maybe let me just see if you can answer it. Suppose I say that we solve okay, a minus lambda I into x equal to 0. We solve this set of homogeneous equation. We solve following set of homogeneous equation. Following homogeneous equation for lambda equal to 3, and we found out linearly independent. Okay, and we found out that there are 7 free. Okay, let's suppose A is a matrix of 20 cross 20. Okay, we found out there are 7 free variables. Then corresponding to lambda equal to 3, how many linearly independent eigenvectors are there? Just try solving this question. So what I'm saying, that when you are solving this a minus lambda into x equal to 0, which is actually bx equal to 0, then you found out, okay, for the lambda equal to 3 when you are solving, then you found out that okay, there are actually 7 free variables, which means corresponding to lambda equal to 3, there are 7 eigenvectors, 7 linearly independent eigenvectors, right? So that's what this question is asking. I hope you understood this question. So let me write the question here. And what is the answer? Just 7. Very easy. Why? Because there are 7 free variables. So that's why corresponding to this lambda equal to 3 also you will be having 7 eigenvectors, right? 7 linearly independent eigenvectors. Now let me just ask a different question. Okay, apart from this, let me just ask a different question. So where I'm saying that if that is a 7 free variables it has, then what could be power of, okay, power of lambda minus 3 in the characteristic equation, right? So what do you think? Let me give you the options. Okay, so let me also give you the options. Let's just shift it here, and the options are, let's suppose the option A is 3, option B is 7, option C is 4, option D is 20. Let me know what are the answers possible. Okay, possible answer, which means this is this MSQ. Just let me know what are the possible answers. See, what is the information that is given in this question? They are saying that you get 7 linearly independent eigenvectors, which means that the power must be at least 7. It must be repeating at least 7 times. So 3 and 4 cannot be the answer. Can the 7 be the answer? Yes. Can the 20 be the answer? Yes also, right? Maybe just lambda minus 3, 20. This is the only characteristic equation. I mean, this is the only factor that you have. But out of this 20, only the 7 linearly independent, that is also fine. Lambda minus 3 power 7 and some other lambda power 13. I mean, you have to make total 20, right? Because the A is 20 by 20. So maybe lambda minus 3 power 7 and some other lambda power 13, and I like the total power of the polynomial should be 20 basically. So 3 and 4 are not possible. Is 7 possible? Yes. Is 20 possible? Yes. So basically it is just like that. If they give you that power is lambda minus 1, power is, let's suppose, 5, then you will say that at most 5 linearly independent eigenvectors, right? In other words also, they can give you this information, they can ask you this information, which means they give you that, okay, 5 or maybe any other thing, okay, let's suppose 7 linearly independent eigenvectors for lambda equal to 2. It means the characteristics equation could be having the power of lambda minus 2 could be 7, because 7 at least 7 times it should be repeating, maybe 8, maybe 9, maybe 10, like that. I mean, it depends on the A. Let's suppose A is 10 cross 10, A is 10 cross 10, then in that case you will be having, okay, let me just write one of the example in just one page so that it is not confusing. So yeah, suppose A is 10 cross 10, then you will be having lambda minus 2 power maybe 7 or maybe 8 or maybe 9 or maybe 10 or till 10. It cannot be more than 10 because A is 10 cross 10. So the polynomial will be, characteristic equation polynomial will be of power 10, right? So if someone says that, okay, 7 linearly independent eigenvectors, okay, let me just go to the next page. Let me ask you the question itself. Let's suppose for lambda equal to 3, 5 linearly independent eigenvectors in A, let's suppose 10 cross 10. Then which of the following are characteristic equation possible? Okay, A is that lambda minus 3 power 5, and then to compensate the remaining, let's suppose you have 5 more, maybe 3 here, 2 here, right? Is this possible? Second one, is this possible? Lambda minus 3 itself 10, okay? And third one, is this possible? Lambda minus 2 itself 5, lambda minus 1 itself 5. And D, is this possible? That lambda minus 3 itself maybe 7, and lambda minus 1 is 1 time, lambda minus 2 is, let's suppose, 2 time. Which of the following is possible? Wherever, see, they have given that 5 linearly independent eigenvectors are there. So at least 5 power you must be having. So this is possible, this is possible, this is not possible because lambda minus 3 is not at all there. And yeah, this is possible. So here A, B, D are possible, right? A, B, D are possible. Again, this was the MSQ that we have. So this is MSQ. So now here A, B and D are possible. So they can give you the reverse information also, which means they can give you that, okay, 5 linearly independent eigenvectors are there in A. Then what are the characteristics equation possible? So this and this is possible, right? I hope you understood. See, if this is 7, then at most 7 you can have. It is not necessary that you will be having exactly 7 or something like that, right? But it cannot have more than 7. That's what we have seen with the examples. I hope that is fine. That's very easy statement. Okay, don't worry it about too much. If lambda minus, let's suppose lambda 1 power m is there, then m, at most m linearly independent eigenvectors will be there, right? At most m linearly independent eigenvectors. So basically this power is called arithmetic multiplicity. Arithmetic, I mean there is just one term, multiplicity. Okay, this power is called arithmetic multiplicity, and corresponding to lambda equal to lambda 1. Okay, how many linearly independent eigenvectors are there? It is called geometric multiplicity. Okay, so this basically there is a term that is called geometric multiplicity. So it basically means that is exactly equal to, not less than or something. It is exactly equal to, the power. Okay, equal to the power. It is exactly equal to number of linearly independent eigenvectors corresponding to lambda equal to lambda 1. Okay, so if someone says that, instead of saying that, okay, number of linearly independent eigenvectors are 5, instead of saying all of this, if they say the GM or geometric multiplicity is something, then it means the number of linearly independent, they are talking about number of linearly independent eigenvectors. So basically arithmetic multiplicity is always greater than equal to geometric multiplicity, because if you have power 5, then at most 5 you can have. Here the geometric multiplicity number of linearly independent could be 1, could be 2, could be 3, could be 4, could be till 5. So that's why this equation hold. Why I'm telling you all of this in short? Because that's not much required. These terms are not required. Nobody has asked in GATE, so that's why like I will keep it optional. Sorry, there are too many optional things like I'm putting here and there, but actually I have to do it like just for the sake of completion. Otherwise I don't want to introduce arithmetic multiplicity or geometric multiplicity, because GATE doesn't directly ask the AMGM. But yeah, these are the technical terms. The power is called arithmetic multiplicity. Number of eigenvectors are called geometric multiplicity, linearly independent eigenvectors. So for example, here, instead of saying that, okay, 7 free variables and all, they can directly say that, okay, corresponding to lambda equal to 3, geometric multiplicity is 7. Then they have asked what about the arithmetic multiplicity? Power means arithmetic multiplicity. So basically this is a question where they have given the geometric multiplicity to be 7. Then they are asking what could be the power, which means arithmetic multiplicity, which is always greater than equal to 7, right? Greater than equal to 7, which means it is either 7 or 20, right? Okay, so anyway, these terms arithmetic multiplicity and geometric multiplicity is not much important, so let's not worry about it. Okay, cool. So I hope that is fine. Now we have covered one very important thing, which is basically number of linearly independent eigenvectors cannot be more than power. Okay, so let me just summarize it. So if I just write the summary, then there are two statements. One is that if lambda 1 and lambda 2 are not equal, then corresponding eigenvectors are linearly independent. This is one statement. Second statement is that if you have lambdas are repeating lambda, right? For repeating lambda. Here the lambdas are not repeating, but this is the statement for repeating lambda. Now, if the lambdas are repeating, in that case, what will happen? In that case, you can say that, okay, let's suppose this is repeating 5 times, then at most 5 linearly independent eigenvectors could be there. Okay, so this is just a summary. I hope you understood. But here the interesting point that we are going to discuss in the next video is that here, if you have lambda minus lambda 1, let's suppose power 5, then as I'm saying that at most 5, sometimes 1, sometimes 2, right? At most 5 linearly independent eigenvectors. I'm saying at most 5. Now, is there a way that I can guarantee that exactly 5? Which means for what kind of matrices I can guarantee that even though power is 5, it still means that exactly 5 linearly independent eigenvectors. eigenvectors, which means that this is arithmetic multiplicity and this is number of linearly independent eigenvectors is called geometric multiplicity. So am equal to gm. So basically there is some special type of matrices for which am and gm both are equal, which means if if that is 5, you get the 5, which means this whatever you see, you really have it. Otherwise you see more, you actually have less. If you are seeing 5, then maybe you are having lesser than 5, right? For in general, that is true, but there is some special type of matrices for that. If you are seeing 5, then you actually have 5 linearly independent eigenvectors, which means that am and gm both are equal. And that's what we will see in the next video. Okay, thank you so much.